In this program, we're going to look at some of the properties of the chlorides and oxides of the period 3 elements. You should be able to see trends as you move along the period. Have a pen and paper handy for making notes. The properties we'll be looking at are the appearance of the substance at room temperature, the reactivity with water, that is how vigorous the reaction is, the pH of the solution. I'll measure the pH after mixing with water to see if any reaction has taken place, and the solubility in hexane. You'll need this to determine the bonding in the substance. The conclusions I want you to reach are: what is the bonding? Are the bonds ionic or covalent? And what is the structure? Is it an ionic solid, a covalent liquid, or a covalent solid? From the results of the experiments, you should be able to determine the bonding in the compound and its structure. Here are some samples of the chlorides of the elements in period 3. In some of the tests I'm going to do, it'll be obvious there's a reaction, in others not quite so obvious. Make sure you have your pen and paper ready for making notes. First, sodium chloride. As you can see, this is a white solid. Now if I put some in the water and stir, nothing very much seems to be happening. No sign of a reaction. The solid appears to be dissolving quietly. But I can check this by looking at the temperature change. The temperature of the water before adding the solid is 22 degrees centigrade, and after mixing it is 21 degrees centigrade. Well, that doesn't represent the sort of change which we normally associate with a chemical reaction. Now, magnesium chloride. This too is a white solid. We've got the hydrated material here because the anhydrous magnesium chloride is not easy to come by in a pure state. And if I stir this, there doesn't seem to be any sign of a reaction, and again it's dissolving quietly. I'll check the temperature, rinsing the thermometer first. 22 before reaction, or before mixing, and after mixing, again it's 22 degrees. So there's very little sign of any reaction there. Next we have aluminium chloride, and we know that this reacts with water, and that's why it's stored in a weighing bottle. If I add a little of this, it's yellow, by the way, because of a trace of iron in the aluminium. 100% pure, it's white. Now you can see when I add this, there's a very vigorous reaction with the water, giving off some fumes. And we can in fact see that the solid, even the solid in the weighing bottle, is reacting with the moist air. Now I can test these fumes by using an ammonia stopper, and you can see there the white smoke being given off, which should tell you what the gas is. To confirm it, I'll put some blue litmus paper there, and you can see that is turning red, which confirms for us that the gas produced is hydrogen chloride. Next we have silicon tetrachloride, and this is an unpleasant liquid, and that's why I'm wearing gloves. It's a clear liquid, and you can see when I add it to the water, there's quite a vigorous reaction. You can also see why I'm wearing gloves and spectacles. And there are fumes given off, which I can test again with the ammonia stopper. And you can see copious white smoke of ammonium chloride. Again, testing with the litmus paper, and you can see that turning red very rapidly indeed. So there's quite a vigorous reaction there. Next, we have phosphorus trichloride, another unpleasant liquid. It's again a clear liquid, and if I add this to the water, not much sign of a reaction at first, but if you watch, you'll see that in fact there is a reaction between the two liquids. I'll see whether there's enough fumes given off to test. Yes, not much doubt about that, but I'll use some blue litmus as well. And there again you can see it rapidly turning red. Lastly, we have disulfur dichloride, and this is a yellow liquid. And when I add this to the water, there seems to be little reaction at first, but you can see the water going slightly cloudy, and also if you look closely at the junction between the two layers, there is some sign of a reaction. The fumes you can see coming in are from the phosphorus trichloride, which is still going strong. Well, now there you've seen quite a definite change in reactivity as you go along the period. And you should be able now to write a statement summarising the reactivity of these chlorides. Now, one of the ways I've used to check on the reactivity with water was to look at the temperature change. But of course, if there's only a moderate reaction and very little material dissolving, then there wouldn't be much temperature change anyway. In this case, we could try another method. We could try measuring the pH of the solution to see if that gives us a clue. A substantial change in pH would confirm that a reaction has occurred. Now, there was very little temperature change for sodium chloride and magnesium chloride, so I will measure the pH of these, and while I'm at it, I'll measure the pH of all of the solutions to see if there's a trend. It's most important to rinse the probe, the pH meter, before doing the test. Now, sodium chloride, when it settles down, pH of 5.8 or 5.9, which is much the same as the pH of the water that we're using due to the absorption of some carbon dioxide from the air. Rinse the probe carefully before trying the next one. Magnesium chloride, pH here. Just wait to make sure we have got it equilibrium established. 5.7. Again, hardly any difference from the pH of the water we're using. Again, I must rinse the probe carefully before doing the aluminium chloride. Now here we've got a very definite fall in pH down to 3.2. Rinse the probe carefully. On to the next one, the silicon tetrachloride. And you can see here that the pH has dropped right down to 0.4, 0.3 even. Rinse the probe carefully. I have to be very careful this time because you noticed there is some solid in this beaker. You should be able to work out what that is. Next, the phosphorus trichloride solution. And here we have a pH 0.6, 0.7. Rinse the probe again. Before doing the last one, the sulfur chloride. And here we have 0.3. You can use these results to classify the elements into metals, non-metals and semi-metals or amphoteric elements. Don't take too much notice of small differences in pH because I didn't control the concentration of the solutions. Now you should plot a graph of pH against the chloride and use it to predict the pH of a solution of chlorine. Now I'll perform a similar series of experiments using hexane instead of water. That should give you some idea of the bonding in the substances. Now you know that sodium chloride is ionic and that's why it dissolves in water. But what about a non-polar solvent such as hexane? If I add some sodium chloride to hexane and stir, there's no sign of the solid dissolving at all. So if the rule of like dissolves like applies, then we might expect ionic substances not to dissolve in hexane, whereas the covalent substances perhaps will. Let's try the rest, and this should enable you to classify these chlorides as covalent or ionic. Magnesium chloride next. If I stir this, again there is no sign of the solid dissolving. Next I'll try aluminium chloride. No fizzing this time. And if I stir, there's no sign again of the solid dissolving. Next we have silicon tetrachloride. I'm still wearing gloves, notice. And when I add this to the hexane, no sign of any vigorous reaction. And if I stir this, you can see there's no sign of two separate layers. The silicon tetrachloride has dissolved completely. Next we have phosphorus trichloride. Again, if I put the liquid into the hexane, and stir. Again, there's no sign of two layers. The phosphorus trichloride has dissolved completely. Lastly, we have the disulfur dichloride. This is a yellow liquid, remember, the most unpleasant smell. And when I put it in the hexane and stir, you can see that the whole solution is yellow. There's no sign of any separate layers. The disulfur dichloride has completely dissolved. Well, from those results, you should be able to work out quite easily the bonding in these compounds. And you should also be able to predict the bonding in chlorine and whether chlorine is soluble in hexane. Now I'll do a similar series of experiments for the oxides of the elements. Again, you should note down the appearance of the compound at room temperature, its reactivity with water, the pH of the solution, and the solubility in hexane. This will help you to reach conclusions about the bonding and structure in the compounds. Now I have here samples of some of the oxides of the elements. There's no sodium oxide here because it is rather difficult to make and store this in the laboratory. So we'll start with magnesium oxide. You can see this is a white solid, and when I add some to the water and stir, very little seems to be happening at all. But I'll check the temperature. The water before we start is 22, and the temperature now is still 22. So there's no sign of any reaction there. Now let's try aluminium oxide. Aluminium oxide is also a white powder, and if I put some of this in the water and stir, again very little seems to be happening. But I'll check the temperature, rinse the thermometer, and again the temperature is still 22, there's no sign of any change. We'll come back to these to measure the pH later on. Next is silicon dioxide, and this is in fact a sample of purified sand, whitish solid. If I put some of this in the water and stir, it doesn't look as though anything's happening here. I'll check the temperature. And once again, the temperature doesn't seem to have changed at all. Now we come to phosphorus pentoxide, and you can see that I've got this stored in a weighing bottle. So you can guess that something's going to happen here. I put some of the solid in water. Well, you can see there's a very vigorous reaction. And on stirring, the solid all dissolves. There's no real need to measure the temperature change here, but I will so that you can make a comparison with the others. And there the temperature has gone up considerably to 33 degrees, confirming that there's quite a reaction there. Well, next we've got sulfur dioxide, and this is a very toxic gas, so we have to be careful how we handle it. I've got a cylinder here of compressed liquefied sulfur dioxide, and I'm going to bubble some of the gas into this tall cylinder of water connected to a gas trap. Now watch when I open the tap. The first few bubbles is just air coming from the connecting tube, and they're passing straight up the cylinder unchanged. As we carry on and flush out the air in the tube, now we're getting sulfur dioxide coming through, and you can see the bubbles getting smaller as they travel up and disappearing altogether before they reach the surface. The gas is very obviously dissolving, and in fact it's a very soluble gas indeed. I won't measure the temperature change, although there is some sign of a slight warming, despite the fact that the gas, as it leaves the cylinder, cools down because of the release in pressure. Dichlorine monoxide is even more unpleasant and toxic, so I won't be showing that one to you at all. Now I'll measure the pH of the solutions, starting with magnesium oxide. And you can see the pH here is about 10.4, 10.5. So although we thought there was no reaction before, it's fairly evident that there has been one. Rinse the probe carefully and move on to the aluminium oxide. And with this one you can see the pH is about 9.1. So once again, although there appeared to be no reaction, there must have been some reaction between the aluminium oxide and the water. Now I move on to the silicon dioxide. And here we have a pH of 6.8, down to 6.6, and that is much the same, still going down a little bit, much the same as the water that we're using. So it seems there is no reaction between the silica and the water. Now on to the phosphorus pentoxide, and here there's a very dramatic change. The pH has dropped right down to 1.5, 1.4. So that confirms a very considerable change there. For the sulfur dioxide, I'll have to disconnect this bung. And move the cylinder over here. Rinse the probe. And the pH of this solution is 1.9, 1.8. You should now be able to plot a graph of pH versus the compound as shown here, and use it to predict the pH of a solution of sodium oxide in water and dichlorine monoxide in water. Now let's see whether these compounds dissolve in hexane. First, magnesium oxide. And I stir this. There doesn't seem to be any sign of the magnesium oxide dissolving. Now let's try aluminium oxide. And again, even on stirring, there doesn't seem to be any sign of the aluminium oxide dissolving in hexane. Now we'll try silicon dioxide. And once again, even after stirring, there's no sign of the silica dissolving. So this compound dissolves neither in water nor in hexane. Now I'll try phosphorus pentoxide. No sign of any reaction this time, but when we stir this, it looks as though perhaps some of it has dissolved. Now let's try the sulfur dioxide. I've got the same apparatus here as before, except that the measuring cylinder contains hexane rather than water. When I open the valve from the sulfur dioxide cylinder, we shall first get a few bubbles of air from the tubing, and they come up to the top. But now we're getting sulfur dioxide, and you can see the bubbles getting smaller as they go up the cylinder, confirming that sulfur dioxide is soluble in hexane. Do you think that chlorine monoxide and sodium oxide will dissolve in hexane? Well, I hope from the results of all these experiments you should have learnt a good deal about the structure and bonding in all these compounds.